Okay, so we've been talking chapter 1 here, and we talked about the atom. We talked about some important experiments that led to our understanding of the atom. Remember that we had some important ones. We had our Thomson, who did the CRT sort of experiments, the cathode ray tubes. We also had Milligan, who did the oil drop experiment. And remember, kind of from both of those, the mass of an electron and really the electron was sort of looked at. This led to sort of an early model of the atom, which is our plum pudding model. And again, that is the model where, as we talked about, we sort of have this positive charge spread out all over. We have these electrons embedded inside. And again, most of the mass of the atom was thought to be made up of those electrons. Later sort of disproven through the next major experiment, which was Rutherford in his gold foil experiment, where he shot alpha particles basically at atoms, pieces of gold foil and other ones. Again, remember that he sort of anticipated what would happen since alpha particles are positively charged radioactive particles, and you're shooting at this sort of jello or pudding of positive charge. He did expect them to go through with deflection as sort of positive and positive as it sort of punches through the pudding part of it, if you will. He was really surprised because what he found was that most of them went through undeflected. But again, every so often we did see ones that bounce off at these really large angles. So obviously we sort of had to abandon the plum pudding model and came up with sort of our current model of the atom, which is protons and neutrons, and that's going to make up this really dense positive core, right, known as the nucleus. Most of the atom is empty space, which accounts for why the particles just went through with no problem. And in that empty space, we do have electrons, and as we'll talk about in the next chapter as well, they are traveling sort of randomly about the nucleus. There is some attraction between, obviously, the nucleus and electrons as they are negatively charged. And overall, really, our nucleus is positively charged because of the protons that are present. Thank you. And that is, again, the current idea of our atom. Also, the major difference was that is the nucleus that is most of the mass of the atom. And the idea there was through experiments, it was found that the neutron is actually the heaviest of all three subatomic particles, followed very closely by the proton. The neutron and the proton are essentially 1,800 times or so heavier than any electron that's out there. And again, that's what makes, sort of the nucleus most of the mass of the atom. We talked about some other important aspects of the atom. We talked about isotopes, and isotopes are, again, the same element, but different numbers of neutrons. And because they have different numbers of neutrons, they do have different masses because of that. Remember that we also have the atomic number, which is abbreviated with a Z, and that is the number of protons there are. Also, that is what we can find on the periodic table above the symbol. That number is the atomic number. Remember that if we do have a neutral atom, it will also tell us the number of electrons. But the definition there of atomic number is just the protons. We also have the mass number, and that is our number of protons plus our number of neutrons, also sometimes abbreviated with an A. And we can use both of these things here, the mass number and the atomic number, and we basically can subtract the two, and that will give us our number of neutrons. Pretty much everybody has protons, electrons, and neutrons, except for hydrogen. Hydrogen only has a proton and an electron. It does not have a neutron, but everybody else will have all three of those particles. Also, remember that the mass number is not found on the periodic table, as the mass number, the atomic number, protons, electrons, and neutrons, they all need to be whole numbers. And on the bottom, there's the atomic mass, which is obviously not whole numbers in most cases. We closed up there talking about ions, and the two different types of ions, which are cations, which are positively charged, and our anions, which are negatively charged. And remember that if we do have some type of ion, the only thing that does change is the number of electrons. As we talked about, out of protons, electrons, and neutrons, it is the protons that is most important, as that determines what element you're talking about. Again, if you look at the periodic table, there is no atomic number that repeats, which means if you know the atomic number or the number of protons, you'll know exactly what element you are talking about. Cations are a result of somebody losing electrons, and that's why they're positively charged, because they have more protons than electrons, so more positives than negatives. And something is an anion or negatively charged because it's gained electrons, which means it will have more electrons than protons, so more negative charge than positive charge, which is why it ends up being overall negative charge. Any questions on that there? So why don't we try a couple more here with some charges? Let's just say we had say we had this guy here. And let's see, we had all right, so for each of these, how many protons, electrons, and neutrons do they each have? Just take a moment and calculate it up. Let's see what you come up with. Okay, so let's take a look. We'll start here. So remember, when written like this, top number is our mass number. Bottom number is our atomic number. So that means in this case, our atomic number there is going to give us our number of protons, which is 28. And again, that's going to be 28 basically positive guys. And in this case here, that means in terms of our electrons, it is positively charged, which means it's lost electrons. And frankly, it has a +4 charge, which means it's lost 4 electrons from the neutral. And a neutral guy would have 28 electrons, so less 4 would be 24 there. That's going to give us a +4 left over, which again is where that charge comes from. And our number of neutrons in this case would be our 60 minus 28, which looks like 32, I think. Any questions on that one there? All right, so if we go over here, once again, that's going to be our atomic number, which is our number of protons, which means there's 16. In this case, it's a -2. Which means it has gained electrons and it has gained 2 electrons. And since we do know that the atomic number and the number of electrons would equal each other in a neutral guy, we could actually use the atomic number here and just add 2 electrons to it because it did gain, and we will end up with 18 electrons. And that's going to give us our -2 left over. And our number of neutrons in this case is going to be 35 minus 16. And that looks like a 19, I think, in that particular case. Any questions on protons, electrons, neutrons with things with charges? So again, as we talked about, just the electrons change. Everything else pretty much stays the same. Yeah. All right. We will kind of wrap up the rest of this chapter, I think. So just talk a little bit about energy. Again, as I mentioned before, they pretty much have taken energy out of this class and moved it to the next class. But again, it will pop up as we kind of go through different chapters. So we talked a little bit about sort of exothermic and endothermic earlier. But again, here, energy is really the ability to do work or produce heat. Heat, as we talked about, does flow from basically one object to the next due to some type of temperature difference between them. And as we talked about, it always does flow really from the hotter object to the colder object. The hotter object, again, will release that energy in an exothermic type process. The colder sort of substance there will gain that energy in an endothermic process for itself. The law of conservation of energy, as we talked about a little bit earlier, we don't create nor destroy any energy, but it can be transformed from one place to the next. And again, in chemistry, we think of energy as sort of this, in a sense, perfect sort of transfer from one object to the next, which essentially means that if somebody is going to lose a certain amount of energy, there has to be somebody that will basically gain the same amount of energy. So again, if like, for example, a big boulder drops down onto the ground, it's going to transfer that energy to the ground when it hits, as it will lose some of that energy as it falls down and hits the ground. The total amount of energy, bless you, is constant in the universe, and that's sort of the idea there. A lot of times when we talk about sort of energy and things like that, oftentimes we talk about sort of the system and the surroundings. And basically, the system can be anything that you're pretty much dealing with. So, if you're doing some type of experiment in a beaker, for example, that would be your system. And then obviously, everything outside of it would be the surroundings. And again, we have just, that transfer of heat and energy from the system to the surroundings. If you for example, had a lit a match or something like that, and you put your hand next to it, right, you could feel the heat coming off, right, to the surroundings where your hand is at. It's going to absorb that energy, which is why your hand feels hot. And it obviously is going to release that energy to the surroundings. Yeah.
So are you saying that energy is not going to be put that much on this first unit test, but it's going to come up like
No, I'm going to say we are going to talk about energy in different parts, but we're not going to explicitly fully jump into the energy chapter, which is, I think, chapter 6 in your book, to be honest with you. They moved years ago, chapter 6 out of this class into 200B. So you actually don't do like the official energy chapter until you hit like 200B. But obviously the people that wrote your book assumed that you would do chapter 6 before you hit all the later chapters. So energy does pop up in other chapters along the way because obviously they assume that you've done it. So in that context, that sort of limited context, will tie energy into what we're talking about. But there's sort of a full-blown sort of energy chapter that you don't do now until 200B. Yeah. I believe that's what it says. So yeah. Yep. All right. So some important sort of types of energy or different types of energy that we come across: radiant energy, thermal energy associated with the random motion of atoms. So thermal energy is related to how much atoms or molecules are present. So the greater amount of thermal energy you will have is based on the number of molecules and atoms that are present. Thermal energy is different than temperature. Temperature is sort of a measure of sort of what's going on. And, just to illustrate that, if you have like a big bathtub, like 40 degrees, and you had like a cup of coffee at like 90 degrees, it's actually the bathtub would have a lot more thermal energy because the bathtub contains a lot more particles, say, of water than it does in the cup of coffee. And it will have a lot more thermal energy. Although the coffee has a higher temperature, the volume of coffee there, right, in terms of, say, water, is very, very small compared to the amount of water that's in the bathtub. So it actually will take a lot more energy to raise the temperature of the bathtub than it would, say, the cup of coffee. So that's why the cup of coffee has a higher temperature, because it won't take as much energy to increase the temperature of that volume, say, of water versus the volume that's in the bathtub. That's something you'll learn about, speaking of that energy chapter, in chapter 6, which is specific heat capacity. It takes a lot of energy just to change, for example, water by 1 degree Celsius. So obviously you have less water in a coffee cup, so less energy needed, results in a higher temperature than, say, water in a bathtub. Chemical energy, there's energy involved in bonds. So when we make a bond and we break a bond, those are processes that occur. So when we make bonds and we break bonds, in terms of energy, if we had to make a bond, it is actually an exothermic process. So if you think about it, you have two things that want to come together to make a bond. They have a lot of energy. They have to release that energy to kind of slow down, and that's going to allow them to sort of come together and bond. and that's sort of an exothermic process. If you already have a bond together, you need to put energy in, which is an endothermic process. They gain energy, and they now have enough energy to sort of wiggle away from each other. Happens just like that. But that is a endothermic process. So when you break bonds, it's endothermic. Energy is absorbed. And when you make bonds, it's actually an exothermic process. And energy is released. Nuclear energy is the energy stored within the collection of atoms. Also something you'll talk about in 200B. I have a whole chapter on nuclear chemistry. And that involves nothing more than playing with everything in the nucleus. So changing protons to neutrons, neutrons to protons, all those type of things. Involves a lot of energy sort of output. Potential energy, as we talked about a second ago, sort of the classic example, right, is the energy due to position. So big giant boulder on top of a hill about ready to fall off has a particular amount of potential energy until it falls off, right? And then it can turn into kinetic energy, right? Which is the energy of motion. It will eventually hit the ground. And as I mentioned before, it will then transfer, right, some of that energy to the ground as well. Again, not losing any sort of energy along the way. So kinetic energy, as I mentioned, is directly proportional to the mass and its velocity. We won't calculate potential energy, but common units of energy are joules and kilojoules. And there are 1,000 joules in a kilojoule. Also, calories, lowercase c, and kilocalories are also very common units of energy. And sort of same relationship, there is 1,000 little calories in a kilocalorie. And when I say little calories, a calorie can be a capital C calorie. And that is sometimes referred to as a nutritional calorie. And that is equal to actually 1,000 of the little calories with the little c, which is the same as a kilocalorie. I would say in chemistry, pretty much most of the time, you're probably going to be rolling with those two units in terms of energy, joules or kilojoules. I would say maybe kilocalories and calories pop in there occasionally, but most of the time, energy is sort of seen in just joules and kilojoules in our case. So a really important relationship between those two is what we see down here. 1 joule is equal to a kilogram meter squared second squared. So that relationship does pop up a lot, and sometimes it pops up a lot in some formulas that we will see along the way, including one in the next chapter. We will see that relationship there. So a kilogram meter squared divided by second squared is equal to a joule. So that's also a really important one to keep in mind. Any questions on that there? And here again are, whoops, come some of those. And again, a joule is the amount of energy needed to move 1 kilogram mass, a distance of 1 meter. And again, this is most likely in chemistry, the two that we sort of see related to each other. It's also equal to a Newton meter. That's what the N stands for. A calorie is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. And like I said, calories and kilocalories are related to each other. All right, any questions on that there? All right. So like I said, as we go through some different chapters, some energy talk will pop in there. And again, we don't officially go through the energy chapter anymore in this class. Okay, so in chapter 2, we're going to talk a little bit more really about electrons here and sort of what happens with electrons as they transition from one energy level to the next. We'll also talk about electron configuration and all that good stuff, quantum numbers and how our orbitals and all those kind of things. So let's talk a little about atomic structure here, and I think the periodic table is in here as well. So one of the ideas of what we're going to be talking about and the main sort of aspect of what we'll be focusing on is the idea of you have electrons that are on these different sort of energy levels. And as you excite an atom, what happens is these electrons will basically gain energy. And they will basically find themselves jumping to a higher energy level. Now, electrons and pretty much everything in chemistry, the more stable sort of situation for everybody, and really the basis why a lot of things sort of occur in chemistry, reactions, for example, um, bonding and things of this nature, is to sort of get into a better state of energy. And usually that involves the lowest state of energy that things can get to. So the lowest state of energy that things can get to is sort of the most sort of stable and things ideal sort of situation that people want to get to. So when an electron gets excited, what will happen is it'll eventually want to kind of work its way back down to a lower state of energy. Now, as we talked about, there is sort of a conservation of energy sort of process that occurs with this, which means in order for it to drop energy levels, it has to give off energy, right? And it will give off energy in the form of a wave of light with a specific wavelength. Now, if that wavelength of that photon of light that's coming off is in the visible part of the spectrum, you will see colors, hence the fireworks picture here. The idea there is when you launch fireworks, they explode, which applies a lot of energy to those elements really quickly that are in those fireworks. Those electrons get excited and then they start dropping back down to a lower state of energy. And the result of that is you'll see different colors as that energy is being given off as those fireworks basically explode, and you'll see different colors and stuff like that. So that is the basic sort of thing that we're ultimately talking about here is these electrons, again, transitioning from one energy level to the next. And we do see different colors because electrons, again, are transitioning from different energy levels, and that energy that's coming off in the form of a wave will essentially be in that visible part of the spectrum. And that visible part of the spectrum, as we'll talk about, is again where we see colors, that kind of Roy G. Biv type thing, the red, orange, yellow, green, blue, indigo, violet type of situation. So let's talk a little bit about electromagnetic radiation and how energy is basically transmitted through space is really in the form of a wave. So as those electrons, for example, are transitioning, it will, for example, give off energy as it goes from higher to lower in the form of a wave. And waves have certain characteristics that we'll talk about. They have the wavelength, frequency, and speed. And as we will see, basically the wavelength is that distance between two troughs. That is our wavelength, which is abbreviated with the lambda symbol. Frequency is basically how many times the wave passes a particular point in a second. And that is sometimes abbreviated with the nu symbol there. And the speed of a wave is basically how far it's going, say, per second, like meters per second, how fast it is traveling. So let's take a look at each of these here. So the wavelength, again, is that distance between two peaks or two troughs when we look at a wave. So really between these two, or it can even be between these two as well. Frequency is the number of waves or cycles that pass per second in a given point in space. So there are certain units associated with these things. I would say for wavelength, meters is very common. Centimeters and nanometers are three sort of common sort of units of waves. A lot of times you do need to get things into meters for everything to sort of work out correctly in calculations. Nano is 10 to the minus 9, right? Centi, right, is our 10 to the minus 2. So these are three common units. I would say most of the time, probably these two units are the ones you're going to see the most for wavelength. I would say most things are given the wavelength in meters. but when we talk about colors in the visible part of the spectrum, it's oftentimes given in nanometers. So when we talk about, this red color, blue color wave, it is given usually in nanometers. So that kind of nano 10 to the minus 9 we use a lot, especially on Monday in the second lab that we're going to do. We'll use it all over the place, but that is a good conversion to kind of know. Frequency, as I mentioned, is the number of cycles that pass a point in a particular second. It has units of typically reciprocal seconds, which is either this or this. And a reciprocal second is also the same as a hertz. And a hertz is a common unit of frequency as well. So frequency units are typically these guys here are the two common sort of frequency units that you see. And the speed of light is 2.9979 times 10 to the 8 meters per second. I personally round myself there 3 times 10 to the 8 meters per second. But a lot of books and stuff will kind of use this expanded number for it. That is abbreviated with C. C is a constant. It is a value that you pretty much always have available to you. So it's basically that number there. And basically, we have this formula here, which is C is equal to the wavelength times the frequency. And if we just look at units, the wavelength does need to be in meters here. Our frequency is reciprocal seconds, and that gives us units of meters per second for our speed of light here. That means that if you know the wavelength, you could find the frequency by taking the speed of light divided by the wavelength. And if you know the frequency, you could find the wavelength by taking the speed of light divided by the frequency. So those are a few ways you could rearrange that equation, and you might need to use it to solve for either of those two things, the wavelength or the frequency. Any questions on that there? So again, once again, a reminder that formulas will not be provided for you, so you do need to know them, yeah. All right, so why don't we try one here? We'll calculate the wavelength of red light. Let's do nanometers. Nanometers. And again, nano is 10 to the minus 9. That has a frequency. Okay, so let's take a look. So obviously here we are looking for the wavelength here in nanometers. We have the frequency given to us of 4.62 times 10 to the 14 reciprocal seconds. And again, that's basically the same thing as a hertz. And that means we can use our C is equal to our wavelength times frequency. And in this case, solving for wavelength, dividing this to the other side will give us C divided by our frequency. Putting this in, I'm going to use the 3 times 10 to the 8 for my speed of light. Again, you can use the 2.9978 to be like divided by our frequency, 4.62 times 10 to the 14 reciprocal seconds. These guys will actually cancel each other out when you do that, and we will end up here with 6.49 times 10 to the minus 7 meters. Remember that we are looking for nanometers here. So again, the proper use of this is in 1 nanometer. There are 10 to the minus 9 meters. So again, not reverse the other way around, which is a very common mistake people make. Using that here, 6.49 times 10 to the minus 7 meters. As we talked about, we want to go opposites to get rid of our units there. So meters are going to go on the bottom and nanometer is going to go on the top. The meter is going to cancel. Also a reminder that that basically is 1 times 10 to the minus 9 if you need to punch it in scientific notation to your calculator. And that should yield you like a 649 nanometers in this case. Any questions on that there? Yeah.
So, solving. It's going to ask for nanometers.
I won't say it will always ask for nanometers. So technically, if it doesn't give you any type of, like, give it in this unit, you could give it in any sort of wavelength unit, meters, centimeters, whatever you want. But a lot of times when you're dealing with the visible part of spectrum, which is the part that has colors like red, blue, green, all that kind of stuff, a lot of times those answers are given in nanometers. Everybody else kind of is a lot of times given in meters and stuff like that. Yeah, other questions? Yeah. All right. That's what we just did. Hopefully they agree. That's good. All right, let's try another one here. Calculate the wavelength of a radio wave, and we could do this one in meters. Why not? That has a frequency of 100.7 megahertz, and mega is 10 to the. Okay, so once again, we are looking for our wavelength here in meters. We are again given a frequency here of 100.7 megahertz. A reminder again that 1 hertz is the same as a reciprocal second, which means we just need to kind of get that to hertz, and that would then be in the proper units there, reciprocal seconds. So we'll do that up front. So in this case, mega would be 10 to the 6. So that again would mean in 1 megahertz. That would be like your radio there. We'll give you 10 to the 6 hertz in this case. So 100.7 megahertz, again going opposite to cancel, megahertz on the bottom, and 10 to the 6 hertz there up on top. And that's going to get us here 1.007 times 10 to the 8 hertz. And once again, that is the same as 1.007 times 10 to the 8 reciprocal seconds. So again, a hertz is basically the same thing. So taking that now, we could use our equation of C is equal to our wavelength times our frequency. Once again, solving for wavelength, C divided by frequency, going to give us 3 times 10 to the 8 meters per second divided by 1.007 times 10 to the 8 reciprocal seconds. Again, those two are going to cancel, and we're going to hit like a 2.98 meters in this particular case. Any questions on that? So again, sometimes people see the word hertz or megahertz, and as I mentioned before, that's basically what you tune your radio to, right? Like 95.5 megahertz is basically what it is, or 102.7. But a hertz again and a reciprocal second are basically the same thing. It's a one-to-one relationship. Any questions on how to calculate those things? All right, so let's also talk a little bit about talk about again sort of waves and energy as well. So there is a relationship between sort of the wavelength, the frequency, and energy associated with those waves. So if we have something that has a longer wavelength, be a lower frequency, that usually is a wave that has lower energy. So that's like something that's just kind of moseying in itself down. Now, if we have a wave that has shorter wavelength, has a higher frequency, that is something that is usually associated with a higher energy. So that is something that's just like moving really fast, right? So, it's like you're in the beach, right? You got the big wave coming, it's just kind of moving kind of slow and stuff like that, right? And you got some waves that are moving really, really fast, right? And they have a certain amount of energy associated with them, especially if you're in the middle of it and get smashed by one of them, right? So waves to come off, depending on the wavelength, will have different amounts of energy. And even in terms of colors, when we see different colors, red versus say blue, for example, they have different energy associated with that. So something like a red wave like we see here has a much larger wavelength than something like green. And blue, for example, has a much smaller wavelength than all of them. So in terms of energy, out of these three, this guy here would be our lowest in energy, as it has a longer wavelength, and blue would be a little higher in energy. And so even within colors, there is sort of a difference in terms of the energy that's coming off as this wave is basically moving through space. So what we are talking about here, obviously, is what we mentioned at the beginning, which is as these electrons transition from different energy levels, they have to, for example, release energy. And just so we're clear, there are two things that sort of are happening when we talk about, actually, I'll go back this way here, draw here, I think. So when we have an electron, for example, at a lower energy level, and it then proceeds to sort of move upwards to a higher energy level, um, that is going to require energy being put in, right? So that is like an endothermic process. So in terms of energy, energy has to be put in, and that's endothermic process. So like we were, for example, talking about in terms of like the fireworks, right? You have to explode those fireworks, right? Which puts a lot of energy into those elements that are inside the fireworks. And obviously it's going to provide a lot of energy needed for those electrons basically to transition from a lower energy level to a higher energy level. As we've been talking about, and most of the time of what we sort of focus in on a lot of times in chemistry is those electrons that ends up in those higher energy levels will eventually want to again work its way back down to a lower state of energy. And that is definitely an exothermic process. And that's what we're kind of talking about when we see colors coming off and stuff like that. That's going to be an exothermic process as the energy is going to be basically given off. And again, that energy is going to be in the form of a photon of light that has a specific wavelength. And that wavelength, again, could fall in the visible part of the spectrum where we do see color, but it could also fall in a part of the spectrum where we actually don't see color. So not all electrons transitioning will result in perhaps colors being seen. Some will be outside of that sort of visible part of the range, but it will sort of account for something else. By the way, this is obviously a very simplified sort of drawing of what's happening, as there are lots and lots of these atoms of these elements, right? So if you had some type of element, you just don't have one atom where it has just like one electron or something like that, right? You got a ton of atoms, right? They all have electrons, they're all getting excited at the same time. And that's why you see different sort of intensity of colors, for example, right? You sometimes see like a darker color, it's really sort of bright type color. Maybe you see a lighter color, and that's the difference in the amount of electrons that are transitioning. So when these sort of transitions occur, be it either a endothermic process or an exothermic process. And by the way, today you'll be doing this process by basically just putting it into the fire. When you put it into the fire, that supplies a lot of energy, right? It's going to excite the electrons. Electrons are going to jump energy levels and give off basically colors in the visible part of the spectrum. So as that energy is being given off, for example, and that is what is sometimes referred to, by the way, when we have sort of those different things happening, when we are talking about electrons transitioning from a higher energy level to a lower energy level, which is an exothermic process, we oftentimes talk about the spectrums, for example, as being emission spectrums, like they're being emitted. So that's what we see. The opposite is like what's referred to as an absorption spectrum when they're gaining energy, and we see that transition that's basically happening. So as these electrons are being given off, they will fall somewhere here on the electromagnetic spectrum. And when we look at sort of the wavelength over here, we have a much longer wavelength. And over here, 10 to the minus 12 is a much shorter wavelength. And as we just talked about, our longer wavelength over here should be our lower energy. And this would be our higher energy side over here. So over here we have like our radio waves. Again, not giving off too much energy as we listen to the radio there on the way in. Um, And if we go next, we then will move to microwaves. And energy is starting to increase here as we go to the left. And microwaves now have a lot more energy, and they have enough energy to make something like water molecules spin really, really fast, which means when you pop your pizza into the microwave, you get it in like 2 minutes and you're ready to eat it. So it has enough energy to get them to spin really fast. Next to that, a little bit more higher in energy, we have infrared, which is sometimes referred to as the IR part of the spectrum. And that's usually where we kind of feel heat and stuff like that sort of coming off. Again, if you had some type of transition that fell in this sort of area, like the one we just calculated, right? Which was like 2 point something, which is obviously in that area there, you're not going to see any type of color, right? And you don't see colors come off as you're listening to the radio in the car, hopefully, and stuff like that. So it's not part of the visible spectrum, those sort of waves that are coming through. Now, when we do get here, this is the visible part of the spectrum. And that is where we see colors, and that is our, Roy, G, Biv, right? And what we do see is there is a difference in terms of energy. Again, in terms of colors, red is lower in energy, and more towards the purple or violet is much higher in energy. So, for example, this does give you, for example, sort of an idea of if you're looking at some type of emission spectrum, for example, and you see a red light sort of come out, or a red line, that's going to result in an electron that probably didn't transfer or travel a lot of energy levels, right? So maybe that's a result of just an electron dropping, maybe just a very short pathway, right? The difference between those two energy levels is not much, and that would result in the energy difference that you see, maybe more like a red, as opposed to maybe you see something in the violet region, and that electron transferred a lot more energy levels, a greater distance, a greater amount of energy, and that would give you something more in perhaps like the violet or purple sort of range. So the different colors that you see in some of these spectrums does correlate to how far the electron's transferring, how many energy levels, and obviously the total amount of energy to do that. Coming next to it is ultraviolet or UV. A lot more energy. That is also why we slap on some sunblock, right, to give you the UV index and all that good stuff, so you don't get too burnt out there. A lot more energy. Next to that is X-rays. Why typically if you've taken an X-ray before, they throw a lead vest on you and they leave the room when they shoot it, right? Because you don't want to be exposed to that much energy and stuff like that. And here is gamma rays at the very end, shortest wavelength, and that's basically just pure energy. Those are one of those radioactive sort of rays, and it's really, really high in energy. If you work with something that's a gamma emitter, for example, gives off gamma rays. You typically have a lot of protection around what you're using, lead and stuff like that. You don't want to definitely be near it for long periods of time because it's very, very high in energy. So this is electromagnetic spectrum, and this is what we're talking about when we talk about, again, sort of this photon of light or wave coming off as the electrons transition. They will fall somewhere here on the spectrum. Again, if they fall in this visible part of the spectrum, you would expect to see colors, but if they fall sort of outside that area, again, you might not see color, but you might observe something else, again, like heat or something like that, if you're in the sort of the infrared area. Any questions on that there? You do need to know this. You don't need to know the exact numbers where everybody breaks off, but you do need to know them sort of in the order of like, put them in order from shortest wavelength to longest or something like that, or highest energy to lowest energy. That also includes the colors in the visible part of the spectrum. You need to be able to put those guys in order of, again, longest wavelength to shortest, or highest energy to shortest, and stuff like that, lower or higher frequency. Any questions on that? Yeah. That's a pickle. I don't know. So let's talk a little bit about energy in the terms of how we see electrons transitioning from one energy level to the next. So there's this idea of what is sometimes referred to as quantized energy. And the idea here is that electrons, for example, particles like electrons, will essentially either gain or lose enough energy to sort of fully transition from one energy level to the next. And that's what the idea of quantized energy is, packets of energy, basically. And you could think about it really as this sort of idea when we talk about quantized energy is like stairs, for example. Right. So if you're walking upstairs or even downstairs, right, you usually have enough energy to get yourself to this step, to this step, to that step, or that step. You usually don't stop like halfway between a step and go, kind of tired, I'm just going to lay it up here because you're going to fall, right? So you either can make it up a step, right, or down a step. You don't stop halfway between. And that's the idea of quantized energy. That's the idea of how electrons sort of transfer from one energy level to the next. So if this electron here is going to move, it's going to gain enough energy to get to this energy level, or maybe it will actually gain enough energy to skip that energy level, get to the next one. Just like walking stairs. Some people could do one stair at a time. Maybe some people could do two stairs at a time, right? Or maybe three. I don't know much more than three, probably. Electrons will gain and also lose energy in that fashion. So if this electron started up here, it will lose enough energy to get fully to that energy level, or it will lose enough energy to pass that energy level and get all the way down to the next one. And that's the idea of quantized energy and how electrons basically transfer. The other type of energy is more of a continuous energy. And the idea of a continuous energy, as we will sort of see in a bit, is like you're walking up a ramp, right? If you're walking up a ramp rather than stairs, you pretty much could lay up anywhere you like along the way. You're going to be fine, right? You don't have to fully get from like here to there. And that's more what is sometimes referred to as sort of a continuous sort of spectrum of how energy is given off. Something like the sun, for example, does that type of thing. Um, and if you have something that's sort of going to, for example, give off a more continuous sort of spectrum, we'll see something more like white light. We'll see all the colors basically coming off at once, for example. Something like elements give off more of a quantized sort of version. And that means that we see very specific colors coming off at specific wavelengths because they correspond to basically, I'm either here or here or here or here. I'm never sort of in between. Now, when we talk about electromagnetic radiation, again, as they transition, they do have to give off that energy in the form of a photon of light. And when we talk about sort of a photon of light, again, is that wave that's basically coming off. But there is sort of this sort of theme that we will see sort of in this chapter of sort of the dual nature of light. And the idea there is particles could have sort of wave functions and waves could have particle-like functions. And, so as we'll talk a little bit further down the road here, electrons, which are particles, can sort of behave as waves and stuff like that. But this energy that we sort of give off is sometimes referred to as a photon of light. Again, it will have a specific wavelength that will correspond to somewhere in the electromagnetic spectrum. And we could calculate that through this formula here, actually. I feel like I'm missing the formula there. So let's talk about how we calculate. E is equal to h times the frequency. And h is what is referred to as Planck's constant. And Planck's constant is 6.63 times 10 to the minus 34 joules times seconds. So that is a constant, just like C is a constant. So if we take this energy, E is equal to H times our frequency, and we take the equation that we saw earlier, which I think should be right about there. That's this guy. C is equal to our wavelength times our frequency. If we solve for frequency, frequency is C divided by the wavelength. So we could take that and substitute that in, and that gives us E is equal to HC over the wavelength. So this gives us really two ways to calculate the energy associated with that photon of light. If we know the frequency, we could basically just times it by Planck's constant. This is definitely a chapter, as we talked about the other day, that you definitely want to make sure you are using your exponent button in this chapter. Otherwise, you're going to be off. So make sure that when you hit these numbers that are written in scientific notation, that you are using your exponent button so that you do punch them in correctly. Also, if you know the wavelength, that's pretty much all you need, because then you can calculate the energy, because h is a constant and c here is the same speed of light that we saw earlier, are 3 times 10 to the 8 meters per second. So these two are constants. So if you know the wavelength, you can figure out the energy associated with that photon of light. And if you know the frequency, you could also figure out the energy associated with that. So those are really sort of three equations that sort of tie together here, and help us calculate those things. Questions on that there? And again, this is Planck's constant here. That is h. So energy does have mass, and that's Einstein's equation, E is equal to mc squared. And as I mentioned a second ago, there's sort of this dual nature of light. Electromagnetic radiation and all matter exhibit both wave properties and particle-like properties, and that's sort of the dual nature of light. Einstein did some experiments known as the photoelectric effect, where again, he was able to basically see electrons sort of being bounced off metal surfaces. And again, this idea of they both have sort of wave-like function and particle-like function. Now, as I mentioned a second ago, a continuous spectrum is really where we see white light, for example, is passed through a prism. It contains really all the visible parts of the spectrum. And again, that is more the sort of ramp idea that you basically can stop anywhere along the way. Everybody's coming off at once. And when we have more quantized sort of energy, we get a more line spectrum. And as I mentioned before, what we will see, for example, is specific lines when you look at it through a prism or a spectroscope, like we'll do on Monday, I think, in that experiment. You will see specific colors, not all blue, but you'll see some different colors coming off at different wavelengths, and they will correspond really to different electrons transitioning different energy levels. The hydrogen emission spectrum is a very common one. You see four kind of distinct lines that develop in the hydrogen one, again, because we have this sort of quantized amount of energy. And here that is, again, you could shine a light through a prism, it will separate it out, and you'll see this distinct line spectrum like we see there on the bottom. And here that is, I think.
When the light emitted by a hydrogen gas discharge tube is passed through a prism, a line spectrum results. This line spectrum consists of light at only 4 wavelengths in the visible region.
So it's going to be very similar to what you're going to do on Monday. You'll look through a spectroscope, which has a prism in it, and it will separate it out. Up here is more of a continuous sort of spectrum. You can see, again, you got all the colors sort of coming off at once. But here we see distinct lines, again, each one representing different electrons transitioning to different wavelengths or energy levels. So in the case of hydrogen, we see these 4 distinct lines. And again, as I was saying earlier, just looking at these lines, we can make a pretty good guess that this guy here, which is red, we know is lower in energy, which means that this electron's probably transitioned a very short part between energy levels, not very far away from each other, so a very shorter transition. Again, here, this is going to be much higher in energy, which means that we would expect perhaps that electron maybe transition a much further path, as again, the idea here when we draw these lines, which represent the different energy levels, the idea of quantized energy is, again, as this guy is dropping energy levels, it'll either end up here, it'll end up here, it will never end up in between energy levels. And that, again, is the idea of the quantized energy, what we just saw there, E = equal to h times the frequency, that amount of energy needed to transition from one energy level to the next. Now, the significance of sort of the hydrogen atoms spectrum is that only certain energies are allowed for these electrons. The energy of electron in a hydrogen atom is quantized, which means, again, as it is transferring, it's got to find itself on one energy level or the next, either gaining or losing energy enough to make those full transitions. All right, so what is the significance of the color emitted from the hydrogen emission? Spectrum is not white. Again, if we did see a white light sort of coming out, that means that basically all the colors of the spectrum is just popping out at once. So you're just going to kind of see that. Here, seeing distinct colors happening at those different sort of line spectrums means that we do have quantized energy here. Again, we can only have electrons transitioning from one energy level to the next. Everybody's not coming off at once, just going to have those distinct transitions, basically, of energy being represented by those distinct lines that you see. Now, this idea of sort of energy and how electrons are moving, and especially with hydrogen, sometimes referred to as the Bohr model of the hydrogen atom. And the Bohr model basically is also referred to sometimes as the planetary model. And the idea here is we have a nucleus and we have these different orbits. I run out of room there. Imagine my circle goes. And, you have like, for example, n = 1, n = 2, n = 3, and so forth. So the idea is we have electrons in these pretty orbits, and they're traveling around in nice, pretty circles. And either they'll be on this energy level, or they'll gain enough energy to be on this next energy level, or so forth, gain enough to be on this energy level, and continuing on. Or as they lose energy, they will transition down and be in one orbit or the next. As we will later see, not really so correct for everything, but this is basically the Bohr model of the atom. Now, the idea here is n is known as the principal quantum number. And that is basically a fancy word for energy level. And basically, n will run from 1 through 7 are the possibilities of n. And an n is equal to 1 is sometimes referred to as the ground state. That is the lowest in energy. It is the closest to the nucleus. So n = 1 is the ground state, is the closest to the nucleus, to the lowest in energy. And anything above that, like n is 2 through 7, these are sometimes referred to as excited states, which are higher in energy. So the idea that Bohr's idea is we have these nice orbits, we have these electrons spinning, or moving around in these circular orbits around the nucleus. And as they either gain or lose energy, they will pop from one sort of orbit to the next. Again, in a quantized fashion, they won't find themselves between orbits. So again, they'll either gain enough to go from, say, the first energy level to n = 3, or they'll lose energy to go from like n = 4 to n = 2. Again, they won't find themselves anywhere sort of in between. And as they do these transitions, obviously, what we would expect to happen, especially as they transition from a higher energy level to a lower energy level, we would expect the atom to release that energy in the form of a photon of light, which will correspond to colors. And they will correspond to the colors, for example, that we do see in the hydrogen atom. And that's what we see here. So, for example, you can see here our red line, just maybe a transition from, say, the third energy level to the second, as opposed to our blue, which is now transferring from the fifth energy level, say, to the second energy level, which is a lot more energy levels, and is going to result in a lot more energy being given off and a higher energy sort of wave, versus our red, which is just transitioning from like one energy level to the next, not a very big drop in energy. a much smaller amount of energy is going to be given off from the atom, and that's going to result in a lower energy wave coming off. And that's what we see here again, our sort of transitioning happening here. So we can actually calculate the energy associated with the electrons that are transitioning from one energy level to the next through this equation here. That is the change in energy. That's what the delta symbol represents, the change. That's the change in energy is equal to, this is sometimes referred to as the Rydberg constant, RH, that's the Rydberg constant, 2.18 times 10 to the minus 18 joules. This is 1 over the final energy level squared minus 1 over the initial energy level squared. So that is the principal quantum number. And this is negative here, right? And this means that if we put some, if we know the transitions, for example, that an electron is going to make, say in hydrogen, we could actually calculate the energy associated with that transition and taking our final minus our initial and again squaring them. When we do this, this is also related to the other equations that we saw earlier, which is, this is E is equal to H times the frequency. This is also equal to Hc over the wavelength. So we could also tie this energy to figuring out our frequency. Could also tie it to figuring out our wavelength as well. So this guy basically, we could figure out our wavelength, could also figure out our frequency here as well. So all those equations basically tie into each other. So what this means is if you know the transition, for example, of an electron from one energy level to the next, you could calculate the energy associated with that. You could also figure out the wavelength of light that's going to come off. You could figure out the frequency of that light that's going to come off, and vice versa. So you could figure out all those types of things. Any questions on that there? And once again, this is technically known as Rydberg's constant, which you could sometimes find on tables. So the idea of Bohr's model, it fit really well for quantized energy levels of hydrogen. It worked really well to explain what is happening in the hydrogen atom. But the idea is it doesn't really hold up as you go past one electron, which is pretty much everybody else. So it kind of falls short after that. It doesn't really sort of account for everything else that we see. And as we will shortly talk about, electrons really don't travel in these pretty little circles and orbits and stuff like that. They travel pretty randomly about the nucleus, but the Bohr model does adequately describe sort of the hydrogen atom and one electron sort of systems, but does sort of fall apart. The idea as well is it sort of falls apart because when you get a lot more electrons involved, you now have a lot of things that are negatively charged near each other and in the same location. So they don't really want to be near each other. And it's a really interesting sort of idea. If you think about it, you have something that has a lot of electrons, a lot of negative charged things near each other, don't really want to be near each other, but still wants to be near the nucleus because it's attracted to it. So it creates different situations that could occur. It also creates situations where energy levels start to switch out and move around a little bit to give everybody enough room to sort of be manageable. So as electrons become more tightly bound, its energy becomes more negative, and as the electrons brought closer to the nucleus, the energy is released to the system. So a reminder that when we talk about energy and you're going to calculate energy, a couple of things are kind of important. When you do calculate energy and you get an energy value, once again, if you do end up with a negative value, you should keep the negative sign for the energy because that tells people it is a exothermic process. And the same thing here, if you calculate it and you do get an energy that's positive, you should obviously leave it as positive. So it does tell you that it is an endothermic process where energy is absorbed. Now, the importance of that is when you sort of tie all these sort of equations together, our E is equal to our h times our frequency, our hc over our wavelength, our minus 2.18 times 10 to the minus 18 joules, 1 over n squared f minus 1 over n squared I. You may hit a negative number for energy, but you may then use that energy value to calculate something like wavelength or frequency. Both of those numbers should always be positive numbers. Yeah. So if you do calculate energy and get a negative value, that's all good. You should leave the negative value. But if you're going to then use that energy value to calculate something like wavelength or frequency, you pretty much should just get rid of the negative value and make it positive, so that you do end up with a positive value for wavelength or frequency. So no negative wavelengths or frequencies, but can have negative energies, and you should keep it negative if it is. So that's something to keep in mind when you do these calculations, because you can't get a negative here, but it does need to be positive. So make sure you get rid of the negative when you use that. So Bohr's model is incorrect, as I mentioned. It works really well for hydrogen with one electron, but it does sort of fall apart. And electrons do not move around the nucleus in these circular orbits. Again, as we will talk about, it does sort of move around in a pretty random type of fashion. There's not these pretty orbits that they're just flying around where you can just kind of put your finger and go, eventually it's going to come back around, right? And going to hit that spot. We actually don't know exactly where they're traveling at any given moment in time. All right, so let's do some calculations here. Let's just calculate everything here. Let's calculate the energy. Let's also calculate the wavelength and the frequency for each of these transitions. So let's take some time and start calculating. Yeah. Okay, so since we're getting towards the end, why don't you finish it up, and then on Monday we'll go through it together, and we'll continue on from that point.